Okay, so this tutorial is on VSEPR geometry molecular shape. So the prevailing theory is called VSEPR, valence shell, valence shell electron pair repulsion. So this is kind of like the key, some of the key, actually the whole thing's key, but electron pair repulsion. So an electron pair, our new textbook refers to these as electron domains. So I might use that term, and I might use the term effective electron pair. But what an electron pair is the number of lone pairs around a central atom plus the number of bonded atoms. So the atom needs like these containers to hold electrons. So what it does is it uses its valence orbitals, or its a valence shell orbitals, and it fuses them together, and it's said to use what are called hybrid orbitals, and the hybrid orbitals make up these containers. So an effective electron pair is a container made with fused together valence orbitals. And so an atom will need, so here's a couple examples. These three molecules actually have the same overall geometry. Their molecular shape is a little bit different because the number of lone pairs and bonded atoms changes. But since lone pair and bonded atoms is actually the same, if you add them all together, these molecules, these three that I'm going to write down, actually have the same overall geometry. So if we look at 4A, a molecule from where the central atom is from 4A, like carbon with four hydrogens, or methane, then if we draw this out, then we get carbon, and it's going to have four bonded atoms. Okay, and it makes a shape that we know as a tetrahedral. So you're going to get, it's kind of like this four-sided pyramid. One, two, three, and then underneath it is actually another pyramid. So this actually has, if we count this up, this is going to have one, two, three, four bonded atoms, which are called BAs, plus zero lone pairs. So total electron domains, or effective electron pairs, is four effective pairs. Okay, the overall geometry of this is called a tetrahedral. Now, let's take a look at the next column over. In 5A, the typical shape of 5A, so we'll just put hydrogens on, like nitrogen, should be 3. And because nitrogen, this goes all the way back to its dot diagram, it's got that lone pair, and now it's got 3 spots where it can connect some atoms. So we'll draw nitrogen like that, and then we'll connect the 3 hydrogens. And then it also has the lone pair. So it needs to have a container to hold the lone pair, and it needs to have containers to hold each bonded atom. So those are there, and then we have the bonded atoms also. So this actually also makes a tetrahedral. The overall geometry of that shape is a tetrahedral. And we get this from adding up this has 3 bonded atoms. 3 bonded atoms, 1, 2, 3, and it has 1 lone pair, so plus 1 LP. So this gives a total of 4 effective pairs, just like we had over here for CH4. Now we have 3 bonded atoms, 1 lone pair, or the same number of effective pairs. So the overall geometry of this is actually a tetrahedral. And if you have this setup, if you have a tetrahedral where you have 3 bonded atoms and a lone pair, the overall molecular shape is called a trigonal pyramidal shape. And the same thing actually happens over here. If you look at 6A, and we have water, then we have oxygen like this, and then we actually have these two containers that hold these lone pairs. So in this case, we actually have two bonded atoms. So I'll write two BAs plus two lone pairs, two LPs, or a total of 4 affected pairs or 4 electron domains. Then this actually, the overall geometry is actually also a tetrahedral. So this is the geometry. The overall molecular shape of 5A is known as a trigonal pyramid. Pyramidal shape. And the overall molecular shape for 6A is known as bent. So these actually, another thing to note about effective pairs and lone pairs. So when you have a lone pair involved, the domain is actually much bigger than the domain is for a bonded atom. So for a bonded atom, for two atoms to bond, their orbitals actually need to overlap. Their hybrid orbitals need to overlap. However, these are going to use when they don't have to be as exact in like one spot in order to share. So lone pairs actually take up bigger domains, and it's actually going to squish these bonded angles a little bit more each time you add a lone pair. So on this one where there's no lone pairs, it's actually going to be, the bonded angle is actually going to be 109.5 between all these atoms. So these angles are 109.5 because of the presence of this lone pair. It actually squishes this a little bit smaller than that. So this one's going to be 107.5. And water has two lone pairs, so it squishes the angle even more because these need to take up more space. These domains to hold lone pairs are much bigger than the domains to hold bonded atoms. Just because the lone pairs are not bonded to anything, so they're just kind of a little bit more randomized, the location of the electrons. Here they need to be much more exact for the orbitals to overlap. So this bonded angle here gets squished a little bit more than 109 and 107. This happens to be 104.5, and that's just because of the presence of the extra lone pair. So stay tuned for part 2. I'm going to end this now, and then I'm going to go over our shape chart for all the different types of shapes that you get based on the number of lone pairs and the number of bonded atoms.